Welcome to 36th lecture on numerical analysis. In this lecture, we will continue studying solution of ODEs, ordinary differential equations, using Taylor series method. Taylor series is a way in which we can represent y as a function of s in terms of y evaluated at a central value x naught, and in terms of the derivatives, the first, second, third, fourth, and so on, the derivatives of y evaluated at the same central point x naught. Right, in our last lecture we also studied a special case where Taylor series of the Taylor series where x naught is equal to 0. We call it Maclaurin series, and this is actually the same Taylor series with the difference that now x naught is 0. So if you put 0 in place of x naught in this series, we come up with this new series, which is a special case of the Taylor series, and we call it equation number 2. Whereas this first equation, the Taylor series, the equation of Taylor series, we call it equation number 1. Right, in our last lecture, NA-35, we also studied that to find the solution of a given ODE, ordinary differential equation, we must be given the ODE and the initial condition if it is the only one initial condition if it is a first order ODE, and we fill items in either equation 1 or 2. If x naught is 0, we'll use equation number 2. If x naught is not equal to 0, we'll use equation number 1. Right, so dy by dx is minus 2xy. It's an example given where the initial condition is given to be y of 0 is 1.8. so this is x naught. So in this case, x naught is given to be 0, therefore we'll use equation number 2. Since x naught is 0, we'll use equation number 2. So in order to put items in this equation, different terms, y of 0, y prime of 0, y prime of 0, and so on, y prime of 0 is readily available to us because it is the initial condition given in the question. Y of 0 is 1.8. So we readily have the first value available right from the initial condition. To find the second value, y prime of 0, we are given y prime is minus 2xy, the given ODE, dy by dx. We can also write it as y prime. So y prime is given to be minus 2xy. So y prime of x is given to be minus 2x y of x, since y is the function of x, and putting x is equal to 0 gives us minus 2x, and if you place 0 instead of x, we get a 0. So y prime of 0 is a 0. Now starting with the given ODE, once again y prime of x is minus 2xy, and we differentiate on both sides. This y prime becomes y prime of x, and here we apply the product rule. Minus 2, the first function as such, the derivative of the second function plus the second function as such, and the derivative of the first function. So if we continue with this and we put 0 instead of x to find y prime of 0, we come up with the value minus 3.6. So now we can start with this as a starting point, and we differentiate on both sides. And when we differentiate y prime, it becomes y prime, y3 primes x, and we apply the same product rule here, and then we put 0 instead of x, and we get y3 primes of 0 is equal to a 0. And then we can start with this as the initial point, y3 primes of x, and differentiate it, and first we rearrange terms and then we differentiate it on both sides. We come up with this minus 2, this whole term minus 4 y prime of x, and if you put 0 instead of x to evaluate y 4 primes of 0, it comes out to be 21.6. so we see that in this particular case the odd derivatives are 0, y prime of 0 is a 0, y3 primes of 0 is also a 0, y2 primes of 0 is non-zero, in fact it is negative, why 4 primes of 0 is positive. So the trend is such that we have odd derivatives equal to 0, and the first even derivative evaluated at 0 is negative, and the second is positive, the second even derivative is positive, the third would be negative, the fourth would be positive, and the trend would go on. But the odd derivatives would be evaluated equal to 0 at point 0. Right, so we just plug all the things. Which things? Y of 0, y prime of 0, y of 0, y prime of 0, y prime of 0, y 3 primes of 0, and y 4 prime of 0 in equation number 2. And we know, if you put that, the first is y prime of 0 is 1.8, this is 0, the third term is minus 3.6, the fourth term is 0, the fifth term is plus 21.6, and we can go on. And if we use these 5 terms, and if we evaluate it like this, y of x, and if we want to evaluate it, this y of x at point 1, x is equal to 1, y of 1 is 1.8 minus, you replace x with 1, this x with 1, the answer is 0.9. But if we, instead of 5 terms, if we include 9 terms, instead of 5, if we include 9 terms, the answer is 0.675. So with 5 terms, the answer is 0.9. With 9 terms, this is 0.675. Now let's see what is the exact solution of this ODE. This is dy by dx is minus 2xy, initial condition y of 0 is 1.8, and if we solve it, taking y on this side, dx on this side, and then integrate it, it becomes log of y, and this x when integrated becomes x squared by 2 plus some constant k. So y is e to the minus s squared plus k, and we can write it as a separate power of e to the k, and e to the k can also be written as a new constant. Let's call it c to the minus x squared. So it's a general solution, and if we put initial conditions y of 0 is 1.8, we can find the value of c. Y of x is c to the minus x squared, putting x equal to 0, y of 0 is given to be 1.8, and we put x equal to 0, e to the minus 0 squared is e to the minus 0, which is mod, c comes out to 1.8. So the particular solution is y of x is 1.8 e to the minus x squared. We studied in our last course. We studied differential equations in our last course. So once we evaluate this y at x equal to 1, the answer is 0.666, which is the exact answer. And we see that using Taylor series method, we reach to a very close value, 0.675, very close to 0.666, the exact answer, if you will use 9 terms. But if we use 5 terms, the answer is very different from the exact answer. So this means adding more terms will take you it will take you closer to the exact answer. So if you use, instead of 9, if you use 10, 11 or 12 terms, you would be closer, you will be further closer to the exact answer, 0.66. Right, so I encourage you to use more terms. In fact, it is actually I want to give it as a homework. Include 10, 11 and 12 terms, and you will see that your answer is further closer to the exact answer, 0.666. Right, that's all for this lecture. Thank you.